Thank you so much. Well, welcome everybody to the second tutorial that I would like to give in this course, which is on the introduction to applications of homotopy theory in the analysis of topological defects and solitonic structures in different types of ordered media. So I would like to give this presentation in a way that hopefully will help you build intuition in how such approaches that of course come from pure math to physical sciences can be useful in understanding different types of topological field configurations. And so I'll again, as I mentioned, try to build an intuition, but perhaps it will not be totally rigorous, perfectly rigorous, as our pure math PIs, would it differently than our pure math PIs would perhaps cover this area, right? And because here our focus is to apply these types of idea for the analysis of real physical systems. So for many people, topology would be associated with topology of surfaces, right? So we know that these types of objects in here have different topology of surfaces that can be characterized by genus or Euler characteristics. But that very idea of the difference between the topology of these surfaces goes all the way back to the Poincaré theorem, which tells us that every closed, simply connected two-dimensional surface is homomorphic to a sphere. And then the surfaces that cannot be simply morphed to a sphere that are not simply connected, it would be different from spheres, right? So if you would draw some circles on a spherical surface like the one in here, they can all be constructed to points. And in a way, this type of surface is simply connected. This is not the case when you take a torus and you draw a bunch of different circles like the ones you can see in here. This cannot be contracted to a single point. And so these two surfaces cannot be morphed one to another in the topological listing. While we can imagine we morph topologically similar surfaces one to another, like the ones of the donut and coffee mug, and we can very easily see how other types of surfaces cannot be morphed one to another. Again, here is another example of that, right? Sphere and torus surfaces cannot be smoothly morphed. What we would want to do today is to develop a similar type of approach in classifying the different field configurations you could have in order parameter fields like magnetizations in solid state magnets, or Director fields in liquid crystals, or polarization fields in ferroelectric materials and other types of systems. The distinct topologies that we will introduce in these order parameter fields will have that similarity to the surfaces that you've seen here that when you can morph one to another, they will be considered being topologically similar, and when you cannot smoothly transform one to another, they will be topologically distinct. And so again, kind of building on that easy, intuitive understanding of topology of surfaces, we can imagine that there will be field configurations like the two defects you can see in here that cannot be smoothly morphed one to another because they will be classified by some distinct different topological invariants, such as genus for surfaces, right? That will make them topologically distinct, right? And then here, this example involves a singular topological defect that two singular topological defects that are different from each other and cannot be smoothly morphed one to another. The other example is a non-singular field that has no regions of discontinuity of alignment of these unit vectors, but yet is topologically protected in this case and cannot be smoothly morphed into a uniform state. And while looking at surfaces like the ones in here, it's very easy to imagine, how the topology of these objects is conserved, right? You literally would have to cut and glue to morph one to another. It is less intuitively easy to understand why these objects are different or similar. So we need some help. And this help will come from the analysis of these field configurations with the help of homotopy theory. So what we will do is do some kind of mapping from physical space or configurational space to order parameter space. And depending on whether these maps are topologically similar or distinct, we will say that the field configurations themselves will be similar or different from each other. And so in physics, we often deal these systems like the ones you see depicted in here, made out of rod-like molecules or some magnetic moments of colloidal nanoparticles, or similar types of ordered parameter fields, right, that will have unit vector or unit director varying somehow in space and form these field configurations that need to be somehow classified for us to understand whether they are topologically distinct or similar. And so in order to be able to characterize them, we can represent the variety, the entire variety of all possible states that these ordered parameter fields can take. And so if I have a unit vector like this M in here, and I constrain its orientations to be in a single plane, then all possible orientations of unit vector in that plane can be characterized by a circle. A circle, mathematicians would denote as S1, which they would also call sphere. It's just one-dimensional sphere, S1. Right? The regular conventional sphere is denoted S2. It's a two-dimensional spherical surface. So this surface, these spheres, multi-dimensional, right? We will extend this notion of spheres across many dimensions. They are all points in some multi-dimensional spaces that are equidistant from the center, right? And so in here, naturally, as we have a unit vector taking different orientations in a two-dimensional plane, all possible orientations of that unit vector are uniquely represented by points on that circle. And therefore, that S1 sphere is the order parameter space or manifold that describes all possible states that this order parameter can take. This is in 2 dimensions. If I go to 3-dimensional space, well, then the unit sphere S2 is the assembly of all possible states that the end of that unit vector can be described by, right? And so therefore, this is now the order parameter manifold for the unit vector in a 3-dimensional space with all 3D orientations allowed. So therefore, the physical systems like liquid crystal, colloidal systems, spin configurations, and magnets can be all described by such order parameter spaces that somehow uniquely characterize them. And so now, before we proceed further, I would like to ask you, well, what's the difference between unit vector in 2D and unit director in 2D, right? So director has this double arrow, right? And so unit vector can take all possible orientations that are described by this circle. Well, for unit director, it seems this order parameter space is twice too large, right, to describe these orientations, because a vector orientation like this and that are equivalent when you have hat-tail symmetry, right? And so therefore, this would be now the order parameter space, which we can characterize as S1 mod Z2, which means that all diametrically opposite points on that circle are identified with each other. And while this order parameter space seems to be different from a circle, it's like half of it. Topologically, it's still circle because these 2 points are identified with each other, and the topology of that object is still circular, as our mathematicians perhaps could confer, right? So therefore, it's roughly the same, even though geometrically it's somewhat different. This is how we can represent our physical systems, right? With the help of order parameter spaces, and you can probably think about many other different types of order parameter fields, with some of which we'll discuss during this tutorial, but you can also identify the order parameter spaces that would somehow uniquely describe them. And you can see from this example that spheres play somewhat special role in this homotopy theory characterization, because many different physical systems can be described by order parameter spaces that are somehow multidimensional spheres, right? And you can see here some examples, right? So therefore, what we will do today is we will learn how mapping from physical or configurational space to order parameter space, which very often will be corresponding to mapping from one type of sphere to another type of sphere, although not always, not universally always, but very often it will be the case, right? And we'll see how this mapping can allow us to distinguish different field configurations with the help of some topological invariants, and will help us to tell apart distinct field configurations and see which ones are the same or similar to each other. So what we have in here in this table is the mappings from pretty much multidimensional spheres, one or multidimensional spheres, to other spheres of different dimensions. And whenever you see a zero in this table, that means these mappings are trivial. Whenever you see something different like Z or Z2, that tells us that you should expect the possibility of formation of distinct topological distinct configurations. Now what we will do next is we will somehow develop a procedure that will allow us to characterize physical and configurational spaces with help of some spheres, and then the order parameter spaces corresponding to properties of the physical order parameter fields with other types of configurations like spheres as well. And so I would like to show you here some of the examples of that, right? So we just had a table, but I can show you specific examples, right? So for example, in 2 dimensions, if I have a unit vector field, right, we saw that the order parameter space for that was a circle, right? And then which is S1 sphere. And then if I have a singular defect like the one you see in here, you can characterize the field configuration around it by encircling it with another circle or S1 sphere. And therefore, you can do the mapping from this configurational space of one S1 circle to another. And with that, you can characterize these field configurations depending on how many times you wrap the order parameter space with the field configuration corresponding to this topological object. And so you can see from this example, as you do mapping from this circle to this circle, you have all possible orientations in 2D of that unit vector here, and that would correspond to all possible orientation on that circle. So you fully wrap it one time. And therefore, it can be characterized by some integer, right? The number of times you wrap it, or the parameter space plus 1 in this case. Differently from this example, if you would do the same mapping for field configuration in here, you would actually wrap it 2 times, because as you navigate this defect by going around it 360 degrees, you see that the vector field actually rotates by 720 degrees, and that would allow you to wrap it 2 times, right? Okay, so this type of mappings that we looked at as examples would actually correspond to the first homotopy group of S1 spheres, which is this type of topological configuration characterized by first homotopy group in here, right? So pi1 also corresponds to sphere, right? But in configurational space. And then this is nothing else but sphere to sphere map, where sphere is one-dimensional sphere in both cases, and therefore you normally associate it with a circle. Well, another type of, yeah.
May I ask you a question? And how do you introduce the minus sign?
Well, we will consider this in just a few minutes. You know, I just first want people to understand, you know, how these maps are related to the, you know, homotopy theory group, groups of different kind, but we will, in a very few, few minutes, we will go in deep details of the thing. Okay, now if you have point defect in 3D, so the unit vectors around it take all possible orientations in 3D. You're naturally surrounded by one sphere, you map from its surface all possible orientations toward the parameter space, which for a unit vector field is again a sphere. So this is a mapping from S2 two-dimensional sphere to another S2 sphere, a second homotopy group of S2 spheres, which is Z. These results, Z or something else, are results from homotopy theory. This is the gift from pure mass, which we benefit from in physical sciences, right? Now, having such results from pure mass, right? We can have an idea whether certain types of topological defects or solitons could exist in physical systems with certain symmetries or not, right? And it seems like, you know, very pure mass might not have much in common with very concrete physical systems like liquid crystals or magnetic solids, but yet you can see it can have very predictive power in terms of what is possible or not. And therefore, it can save time of physicists who will not maybe need to search for some defects if they cannot be possible, or maybe can help understand what they find in their experiments. All right, well, following this example I gave you, right? When you see such a table, Pi1 or say S1, that means you are mapping from one type of I-dimensional sphere to another I-dimensional sphere. In this example, I in both cases is equal to 1, and the I is equal to 1 and N is equal to 1. And then for this example, both I and N are equal to, but for example, for Hopfians, as we will see in a little bit, the configurational space will be hypersphere S3, and the order parameter space would be S2. Right? Okay, so now let's discuss the procedure, and this will be addressing question that we just got as well. We need a procedure that will do it systematically and allow us to characterize field configurations regardless of symmetry, right, of these fields. So here's the procedure. We identify the ground state manifold or degeneracy of order parameter space of the particular physical systems. For example, you can have different types of magnets, right? You could have magnets where spins can only point up and down, and then you would characterize them with what type of a sphere or what type of order parameter space.
0 dimensions.
As 0, correct? That's just 2 points equidistant from center, right? Or you could have a magnetic system that allows only 2-dimensional orientations. And in that case, as we already saw, would be a circle, S1 sphere. Or it could be a 3-dimensional space, then it's S2. So that's the first step of procedure. We characterize a physical system and see what is the order parameter space that describes all possible values of order parameter. And then we map the order parameter from the sample to the order parameter space. And sample here, it's kind of in more general terms, because as we will see in a little bit, sometimes the physical space may need to be compactified on some configurational space. And then we identify topology of the maps that we are doing, right? So which can be characterized by some homotopy groups. And then we can judge whether these maps can be morphed one to another or not. So therefore, they are the same or different from each other. Okay, so looking at this example, right? So here somewhere we have the physical space. We have some values of the order parametric fields, and we will do this type of mapping to the order parameter space. Sometimes, depending on dimensionality of the different topological objects, like singular point defects or line defects, we will need to encircle them with certain surfaces, like multidimensional spheres. But in each case, characterization of these defects will need to involve mappings, right? And as we already saw for many unit vector fields, all unit vector fields, regardless if they are magnets or characterizing magnets or ferroelectrics or some other systems, the order parameter spaces will be multidimensional spheres. So let's now look at some examples I have in here. So suppose your material will look like this, and everywhere the spins in this case would point in the same direction. All the whole three-dimensional space in this case can be mapped to just one point, as we see, right? So material sample can be huge, but just one point is enough to characterize the values of order parameter that you have in there. And in this example in here, the only difference is it's a different point, right? But again, the orientation of that unit vector does not change in space, and therefore the mapping is, giving us just a different point in this case. Okay, so here I have some examples, questions for you. And in some way I already answered them with the examples we looked at before. So if you have a ferromagnet or ferroelectric, and you have either magnetization or polarization confined to two-dimensional space, right? So on the two-dimensional orientation is supportable. What's the order parameter space? S1 sphere, so as we could see. And then if we have an Eisen ferromagnet, so the magnetization can be up or down, then the order parameter space is S0, right? And so that's just two points that are equidistant from each other, or what we draw. For example, another physical system, superconductors and superfluids can be also characterized by S1 circle. So now let's imagine we have something more complicated. Well, first of all, you could have a disordered state. Then you cannot characterize it with the order parameter space because you don't have much order. But if you have these ordered space configurations depicted in here, you can see in one case, in 2D, right, you will have just one point. The order parameter space here is a circle because these unit vectors are allowed to take any orientation in 2D. They just happen to point in one direction. So therefore, it's just one point on a circle. In this case, they happen to point in a variety of different directions within that plane. And therefore, as you will do a diligent mapping from that space to the order parameter space, you will have some fragment of that S1 circle covered. But yet, your intuition probably already tells you that this is still homomorphic to that state because you could smoothly morph one to another. So you do not have topologically distinct field configuration, even though geometrically these two are quite different from each other. Okay, so now let's take a look at liquid crystal in three-dimensional space, right? So we by now, I hope, understood how unit vector fields can be characterized by S0, S1, S2 spheres, right? Depending on dimensionality of the physical systems. But if you have a director field, from the early example that I gave, you saw if lines of director field are confined to two-dimensional plane, that was just a different circle. S1 mod Z2 with diametrically opposite points identified, but topologically still similar to a circle. If now, however, your director and molecules are allowed to take all possible three-dimensional orientations, for unit vectors, that would be S2 sphere, right? How about unit directors? Well, it is S2 sphere with diametrically opposite points identified, so S2 mod Z2. But it's now not quite equivalent to another S2 sphere, right? And it's actually equivalent to the projectile plane RP2. So we will see that that difference between non-polar director field and polar unit vector field is very consequential, in particular in relation to topological objects of the first fundamental group, such as destinations or line defects in these systems. So again, we can present those this order parameter space in different ways, but the important thing is it's a unit sphere with diametrically opposite points identified. And if you visualize it as a hemisphere still on this equatorial plane, you need to identify the diametrically opposite points. So up to now, we just looked at some unit vector or director fields, and we did not think about any positional ordering at all, right? So the order parameter was just describing some orientations of vectors or directors. But we can also have ordered media such as crystals. And in here, we know very well that we have some repeat units, unit cells that you can translate in space, and you can recreate the whole material from just translating the unit cell and repeating it, copy pasting it more or less many times. In this case, therefore, when we will make some displacements, they can be represented in this fashion in here because of the periodicity of the system. And so pretty much you can think about this as some, depending on symmetry, square or rectangle, right, with periodic boundary conditions, right? And periodic boundary conditions mean that, if you have that rectangle, you first can identify two sides of it and connect them with each other. In that process, you naturally can imagine you get a cylinder, right? And then, the edges of that cylinder also have correspond to periodic boundary conditions, so they can be identified. And as you then connect them, you get nothing else but the torus. So this torus is a two-dimensional surface, right? T2, as it would be denoted. And so now the order parameter space would be characterized by such two-dimensional surface of a torus. So we can have defects of different dimensionality, and they can be classified based on that, and therefore the general procedural mapping that we started to discuss can be applied in slightly different ways depending on dimensionality of these defects. So when we have point defects, like the one we looked at earlier, right? We will be encircling them by two-dimensional surfaces. When we have line defects, and these line defects could be in orientation or molecular alignment or unit vectors, naturally, because they are lines, translationally invariant, we will be encircling them by S1 surfaces or circles. And when we have wall defects, these are two-dimensional planes, it suffices to insert them by S0 spheres, right? And so you can see in here that therefore the configurational space that will allow us to characterize these defects of different dimensionality will be different. So in the case of point defects, it's natural to surround them by S2, two-dimensional sphere. In the case of line defects of different kinds, like dislocations or disclinations. So dislocations are defects in translational order of crystalline solids, like the one you can see in here. Or you could have disclination when it's just a defect in orientational fields, such as unit director field. And then for the case of walls, like in here, which is formed in this Ising paramagnet, right? You can characterize it by effectively surrounding it by S0 spherical surface. And so then, as we already discussed, we need to analyze defects based on maps from physical configurational space to the order parameter space. And oftentimes, as we discussed, these are maps from one type of sphere to another. In this case, from one S2 sphere to another S2 sphere, and therefore they can be denoted as pi2 of S2, second homotopy group of S2 sphere. In this case, is equal Z, which means integers, right? This example here would correspond to ferromagnet, in which case those would be block points, would correspond to ferroelectric, or more or less any other polar system, and that allows for three-dimensional orientations of unit vector field. So the labeling of these homotopy groups sometimes is capital pi or small pi. It just depends on preferences or locations, and we will interchangeably use it too. So they denote the same thing. And so when we do this mapping, and like in this case, mapping from this radial field configuration with all possible orientations of unit vector, we would have all points on S2 sphere or the parameter space, so full rapid, right? That integer Z for that specific case would be just simply 1. But we can also yeah, and so this notation, as we already just discussed, simply classifies a map that we are doing. And so in again, so this table that you see here, which describes homotopy groups for different sphere-to-sphere mappings that we can have, tells us, what defects and what topological solitons are possible. As we have these multidimensional configurational spaces corresponding to I-dimensional spheres and order parameter spaces corresponding to n-dimensional spheres. So now let's look at these examples where we have some integers characterizing topological topology of field configurations, much like the integers, the number of poles or genus characterize two-dimensional surfaces, right? So as we would surround all of these defects and map them to the order parameter space, we would get different, the sphere would be wrapped different number of times. But the wrapping direction can be different, right? So that could define sign. And the number of times you wrap that sphere with this field configuration could also be different. So therefore we can have different integers. And so now what's important is you can see that some configurations can look quite geometrically distinct, like these two, yet the fact that they have the same integer number characterizing them tells you if you try hard, you can morph one to the other. It may take time, but it's possible. And on the other hand, the ones that have different integers you see here cannot be morphed one to another, no matter how hard you try. Okay, so, but in these cases, I had the unit vector fields, and you could naturally see that the wrapping directionality could be different. And we will see some more examples of that in a few minutes. However, if you have line fields, then you can realize that the defects that for vector fields would correspond to different signs, like the one in here and the one in here, correspond to integers of opposite signs. So one is the source, another one is the sink of the field, right? And they would kind of cancel each other if you put them in some far-field uniform background. They can annihilate and disappear because of having opposite signs. If you go now to the director fields, you realize you have non-polar symmetry. So the two configurations that we just looked at would be exactly the same, and these two would be exactly the same because you have that non-polar nature. And so therefore, when it comes to non-polar liquid crystal director fields, this type of defect has a charge that is plus and minus 1 at the same time. And this type of defect has plus and minus charge at the same time. Yet, not necessarily it can annihilate with itself, right? The fact that it has plus charge and minus charge only reflects the fact that you can vectorize it in two different directions. You could draw your arrows pointing inward or outward, right? And then effectively you would have different charge depending on the convention that you use. But it cannot annihilate this another defect of exactly this type if you somehow misuse the convention. So the procedure typically is that in your texture, which can have many such defects, you adopt the vectorization convention. And then if you flip the directionality to the opposite, all defects change their signs. But when you have one directionality of vectorization or the other, they're all much like defects in unit vector fields. And therefore, at that point, in the vectorized director field, the ones with opposite charges can annihilate and vice versa. Right? So, however, the important point is that in the molecular alignment field, the opposite directions of unit vector are not distinguishable because of Cantel symmetry. And so therefore, locally, these defects can be characterized as +1 or -1. However, with global vectorization, you can have annihilation of the ones with opposite charge. Also, they can be represented with the help of, for example, the ansatz expressions for the components of this unit vector field that you can see here. You can easily construct such defects. As we discussed, the important point in characterizing the defects in liquid crystals is paying attention to that property of the point defects, right? And so therefore, the second homotopy group of S2 mod Z2, so spheres with a diametrically opposite point identified, is described, denoted in here in this one. So in other words, locally, these defects have different, have plus-minus charges, but in order to see how they can annihilate or interact with each other, you need to vectorize the texture globally. Okay, so let's now go to lower dimensions and characterize these two-dimensional defects in a ferromagnet. So here we can have such singularities in two-dimensional field. And as we already looked at before, as we would be mapping from the configurational space and circling this point singularity into D and here to the corresponding order parameter space, right? We will be wrapping these order parameter spheres or S1 circles integer number of times. And so these two correspond to wrappings 1 and 2. And, the third one, you could imagine more complex configuration that would wrap it 3 times. However, what would the mathematical result of wrapping spheres around spheres is very general, and you can illustrate this result also with something like rubber band, right? So if you have a closed loop made of rubber, you can wrap it around, say, your finger, which has a circular cross section, integer number of times by stretching that rubber, right? So mathematically, that's equally true for that rubber band and for this field configuration. So of course, it's a bit more challenging to see it for these fields, but you can think, in terms of analogy as simple as this rubber band. But okay, in here we looked at the configurations that would correspond to vector fields in 2D. And Andrei, answering your question, to get the opposite sign, you would just have, what would you have? So we'll see in a little bit. In order to get into the -1 singularity, you could have defects like we will see in a minute, right? One second. So imagine somewhere here, the field is not defined. But it's defined everywhere else, except for this point. I draw it a little bit extended region, but you can imagine this point would have a negative sign in two-dimensional unit vector field. So as you would encircle it by some S1 sphere and map that to a unit circle, you would see that as you go around this circle 360 degrees, the rotation will be opposite to the direction of navigation.
Of course, I know the answer.
Yeah, but
the question about convention,
Mhm.
because you always make this circle counterclockwise. This is convention, right? Because you can go clockwise, and then you will see that you
Convention is counterclockwise,
Clockwise,
but,
and then-
it's just a convention. All right, well, so now let's go to, so before we looked at the, unit vector fields in 2D, but now let's look at, unit director fields. And so in here, we should remember that interesting peculiar nature of order parameter space kinematics in 2D, which was S1 mod Z2, but that's just equivalent to another S1 that just has 180 degrees rotation, right? So normally, we would rotate 360 degrees and only then get to the original orientations, right? But if you have unit directors that have that symmetry, only rotating by 180 degrees brings it to itself, right? When you rotate the rod, 180-degree rotation gives the same rod or the same cylinder. And so indeed in here, therefore, these circles that you see here would be such peculiar circles, right? That 180 degrees corresponds to that rotation. And therefore, even though as you would take such a two-dimensional defect in 2D orientations of director field, and you would go around by 360 degrees, right? The full navigation circle, you see director rotating only 180 degrees, but in order parameter space, your circle only has 180 degrees equivalence of it, and therefore this configuration would fully wrap it one time. And therefore, in terms of homotopy theory group presentation, that corresponds to an integer of 1 in here. Whereas if you would have a radial 2D defect like this, that 360 degrees rotation of director would wrap it 2 times. And then you can have other integers that correspond to z and p. And so, however, here I should make a disclaimer that this is the homotopy theory view on defects in 2D in liquid crystals. There is another convention where people would characterize these defects by mapping it from this circle, not to that, I would say pure mass defined circle, but regular circle. And in this case, I would see that, you already covered half, so this would be half integers. So they would associate 1/2 plus 1/2 charge with this kind of defect, right? A winding number. And so that one should, however, relate to 1 in the homotopy theory type of presentation. Right? And so now the question is, could we have line defects in a unit vector field in 3-dimensional space? And so the line defects in 3D, right, can be encircled by a circle, so that somehow corresponds to the cross-section of that line defect. And all the parameter space for 3D unit vectors is S2 sphere. Right? So now, if you would do the mapping, you would realize that such defects are not possible actually, because the all possible configurations from defects in 2-dimensional cross-section would end up being some forms of circles that you see in here, and you can contract these circles to a single point, right? Which means eventually you could go smoothly to a uniform orientation state, and there would be no defects. So indeed, the homotopy theory from pure mass analysis tells us that that should be 0. And you can again, like before, we were thinking wrapping a rubber around our finger integer number of times, right? Our rubber band could be stretched and integer number of times wrapped around the finger. And here, the intuition tells us it's not possible to, laser a ball is a rubber band like this, right? So, and you can always contract such circles to a sphere. And so what does it correspond in actual physical space? I can create such a line defect just by drawing geometry, right? And yet I can see here there is a singularity, and locally I encircle. It looks exactly the same as the singular point singularity we had before that was described by first homotopy group of spheres, Pi1S1. In that cross-section, it's exactly this. But once I allow these unit vectors to tilt out of that plane, so it takes 2-dimensional orientations, that means you go from the order parameter space being a circle now becoming a sphere, S2. You will see that I can smoothly rotate all of them, and then I see no singularities, no defects at all. That corresponds to, representing that whole state with a single point in the order parameter space. And so this is geometric visualization of that contraction of the circle on a sphere that we looked at earlier. Now, in a similar way, I can do this for line for line director fields, right? In 3D, when molecules of liquid crystal or director field is allowed to take all possible orientations. So I will again, let's say for this radial configuration in some cross-sectional plane, right, tilting all of these directors uniformly, I contract to a single point, so there is no defect left, and this is therefore also topologically unstable. And well, the outcome of this analysis is that in unit vector fields, you can have no singular line defects of first fundamental homotopy group elements in vector fields. Well, that's kind of discouraging result, right? Because nobody should search for them. They are mathematically impossible. Because topologically they can be always smoothly morphed to the uniform state, you cannot find them as topologically stable objects in unit vector fields like magnets or ferroelectrics. However, the result for liquid crystals is different. When our order parameter space is not S2, but S2 mod Z2, while these type of defects can be smoothly morphed to uniform state, so this loop can be contracted to a point, the half integer ones that well, the ones which have only 180-degree rotation of the director around the defect line core are actually topologically stable. And so the reason in this case is that remember that diametrically opposite points are identified, and therefore they kind of pin the particular orientation. So if I will have some point in here with which I draw the circle, that point also corresponds to the diametrically opposite point, and I cannot contract it to a single point somewhere else. And so therefore these type of defects are possible. And indeed, no matter how you would try to rotate all of these little rods, you can never get a uniform state out of this configuration. It will always have some line or wall singularity that you will end up with. And so these type of defects are topologically stable. So the results of the homotopy theory group analysis, I somehow don't have it in on this particular slide. It would be pi1 of S2 mod Z2 is simply equal Z2. And what this tells us is there is only one type of defect lines in three-dimensional space that I can have in addition to trivial uniform state. So in other words, as I can change geometry of this configuration around such a line defect, its topology will not change. And we will see the specific examples in a few minutes to prove, to see that there is only one type of defects in three-dimensional space, even though in 2D, we could see I could have any integer, right? Many point singularities in 2 dimensions. In 3 dimensions, there is just only one. And so we can also do similar types of homotopy theory group analysis for the dislocations in solid crystals. So they could be also in smectic liquid crystals, right, which would have one-dimensional quasi-long-range positional order, or in columnar liquid crystals, right? So in here, as we already discussed, the order parameter space is a torus, and we would need to encircle our singularity, which is this line perpendicular to the screen, by a circle, which in this case is often referred to as Boulder circuit. And then we would do the mapping from that circle to the order parameter space. And then we can have the result is that this type of mapping can give us non-trivial structures. Moreover, we can have, as we know well, edge dislocations and screw dislocations. They will correspond to different types of wrapping of this torus, so different types of circles that can go either around, through the hole or around the hole of the torus, or goes through and around, as depicted in these cases when you have different types of defects. So the number of times you encircle torus going through the hole or around the hole is characterized by these two integers. And this is describing the entire set of possibilities that we could have for these types of singular defects. So up to now, we discussed singular defects, and they had some form of discontinuity in the ordered structure, right? Either in terms of orientations or possessions, yet we can have topologically non-trivial solitonic field configurations where the field is everywhere continuous, yet it's topologically non-trivial. So the simplest type of such topological solitonic structures are the solitonic domain walls. So in here I have two examples. One of them is non-trivial and the other one is trivial. So imagine you have R1 space, one-dimensional space, and then you have unit vectors which are confined to two-dimensional plane, which is corresponding to this plane that we use in here, right? So imagine that these unit vectors are rotating by 360 degrees as you go from one side to the other. In this case, in the two ends of this R1 space, we have the same orientation of this unit vector, right? And therefore, this order parameter space can be compactified on a circle. So you could connect the two ends of this R1 space and compactify it on a circle. And therefore, you would then be mapping from that circle corresponding to this physical space, which is pi1, to the order parameter space, which we already know for two-dimensional unit vectors is S1, right? Or unit vectors into D, and that corresponds to Z. So this is now solitonic wall, which is described also by the first homotopy group of S1 spheres, similarly to how we were using this notation, this very same notation for describing line defects into D, right? In that case, singular defects were encircled by a circle. In this case, however, we get the circle from connecting the ends of R1 space because of doing one-point compactification due to uniform particle background that this physical space has. Now, so this structure is non-trivial, as indeed confirmed by this mapping in here. But you could rotate your unit vectors differently. First, in one direction and then in the opposite direction. And then you get to the very same particle background, right? In this case, however, this structure is trivial, as we can confirm by little rotating these spins and smoothly morphing it to a structure that would have only uniform configuration of unit vector fields everywhere. And indeed, as you would map this configuration from that circle that describes this one-dimensional configuration of space to another circle of order parameter space, you would see that in the order parameter space circle, you would, first go, one way and then turn back and get to the same point, right? So you did not really wrap that order parameter space at all. Which would then correspond to z equals 0 for this type of configuration. So we can have such solitonic walls in unit vector fields or unit director fields. For unit vector fields, in order to get back to the same far field background, we need to have 360 at least rotation, right? And as I already mentioned, because of that background being uniform, we can do 1 point for simplification. So that far field background becomes 1 point and gives us the configuration of space described by S1 sphere. And then the mapping is from spheres to spheres, as we discussed before. When we have a director field, we do not need 360-degree rotation to have a solitonic wall. 180-degree rotation is enough because you can see you get to the same uniform state after just 180-degree rotation. And that again corresponds to mapping from the circle that you get by identifying the far field background orientations, which corresponds to only 180-degree rotation, to another circle, which is order parameter space with such 180-degree rotations. And the result of mapping is the same, right? So phi1 S1 equals Z, but the definition of circles is a bit different. And so in a similar way, we can, have solitonic structures also in high dimensions when we allow director or vector take three-dimensional orientation. And so what's important to also realize that as we have liquid crystals, when it comes to solitonic structures, in 2 dimensions, you can have singular defects that in unit director fields are allowed, but in unit vector field are not allowed, right? So any of the structures where I had only 180-degree rotations is non-orientable, and therefore in unit vector field is not allowed. However, when it comes to solitonic structures in 2 dimensions and higher, you can smoothly vectorize the unit director field, and every solitonic structure that you have in director field is also solitonic structure in vector field, right? So indeed, also in real physical system, we can do this analog of vectorization, right? For example, doping liquid crystal with such magnetic nanoplates that have magnetically monodomain moments, monodomain structure, and therefore well-defined magnetic moments that can vectorize director fields, right? And that can confirm that the theorem that is coming from pure mass that tells us that solitonic structures in director fields in 2 dimensions and higher are also ones in vector fields that allows the dimensional rotations of director. Okay, before we looked at solitonic walls, and we could see very easily how they have this topological non-trivial yet continuous structure, no singularity, right? But now let's see in 2 dimensions. So you've seen these type of structures many times in Grace's presentation in particular as well, right? So, okay, now these are the physical space in here is 2-dimensional, or R2 in mathematical notations, right? The far field background is uniform, just like for 1-dimensional solitonic walls. In the periphery far away from such a structure, the spins, so unit vectors, point in the same direction. And therefore, this R2 physical space can be compactified on a sphere. So just like R1 could be compactified on S1 by taking the 2 endpoints of this R1 space and connecting them, the 2-dimensional R2 plane can be compactified on S2 sphere, because you could just simply say that all of these edges of it, have the same orientation, and you can stitch them together, right? And that gives you topological sphere. Geometrically, it may look a bit different, right? And so then that means when we will be mapping from R2, this is analogous from mapping from S2, because R2 with uniform far field background is equivalent to S2, right? So now we will therefore describe all the possible solitonic structures in 2D that have 3-dimensional orientations of unit vector field allowed by the elements of the second homotopy group of S2 spheres, right? And now, the same mappings correspond to the same charges, integers in here, and therefore the structures that can be walked through one another, and vice versa. When these integers are different, they cannot be walked through one to another. So and again, we can have solitonic structures in director fields and in vector fields. But as we already discussed, the theorems from pure math tell us that you can vectorize such solitonic structures in 2, 3D, high dimensions, and they have the same topology to unit vector field, so you still retain the solitonic nature. So the topological solitons, such as 2-dimensional fermions or baby fermions, they also called, can be characterized by integers that correspond to full wrapping of the order parameter space as to sphere when you do this type of mapping that we discussed. But you can also have structures that wrap it only partially that sphere. Then they are topologically, so they are just fractional fermions, right? They are not characterized by integers, and therefore nothing prevents you morphing smoothly one to another. On the other hand, you could also have multiple integers for certain structures, such as, for example, the configurations you can see in here that are often referred to as fermion banks. 2D configurations with 3D orientations of unit vector field allowed. And if you would map from such a structure field configuration to a unit vector sphere, you would wrap it integer number of times. So you could have also such structures in unit director fields. So in other words, what we looked at up to now were different types of topological distinct configurations. We represented singular defects and topological solitons with the same type of elements of homotopy group, but of course they are structurally very different but they are characterized by similar types of methods, right? And oftentimes we can have geometrically very different configurations, like block and kneel types of two-dimensional skirmings with different configurations, but they can be morphed one to another as long as they're characterized by the same integers. And indeed, this can be confirmed by, characterizing these field configurations of order parameter space. And you can see that one can smoothly morph one to another, both when you deal with spins or unit vectors in physical space or order parameter space, right? So all it takes is smooth continuous rotations, and you can go from one to the other and in between two with different types of mappings that we can have. And so up to now, we, however, discussed these different elements, right? Of the first and second homotopy groups, both singular defects and solitonics, but we can see in here that we also can have elements of the third homotopy group, and that are topological non-trivial, as well as, higher order homotopy groups, some of which are a bit kind of impractical for us to see, at least studying, condensement type of physical systems, although they are common in other physical systems in mathematical theory. But what are these two different types of objects that we have in here? So the elements of the third homotopy group of S3 spheres are the grown-up skirmions, or the original skirmions that were introduced in the Skirm model in particle physics, where the S3 order parameter space actually corresponds to SU2, and the pi3 corresponds to three-dimensional physical space, which can be compactified on hypersphere S3. So R3, just like R2 could be compactified on S2, and R1 could be compactified on S1, R2 on S2, R3 on S3. And so these are the types of topological solitons. But the ones that are described by the third homotopy group of S2 spheres are three-dimensional solitons with uniform far field background. That's why S3 and R3 are equivalent, that are called Hopkians. As we would go through all of these examples, right, we discussed that when we have physical spaces with different dimensionality, but uniform far field background, they can be compactified on compact spaces of corresponding spheres, and we could understand these topological solitons we see in here. Okay, so one important point before we discuss the Hopkians, that the solitons that are these elements of the third homotopy group of S2 spheres. I also want to point out that this equivalence in homotopy theory group description between point defects and two-dimensional topological solitons, shows up also in coexistence of these structures in real physical systems when we form the so-called torons. So in a structure of toron, which is three-dimensionally localized field configuration, we have a 2D skirmion tubes that is ending on point defects of opposite sign. And so indeed, in this case, you can see the cross-section of this skirmion tube is described by elements of the second homotopy group of spheres. And then the endpoints are also described as point singularities with exactly the same homotopy group and the same elements that would correspond to integers of z, which in this case would be 1. And so in this structure of a toron, therefore, we have 2 point defects of opposite signs, one of which is the source and one of which is sink. And then the solitonic structure exists in between two of them. Importantly, you can, analyze it with the help of so-called pre-images that characterize regions in space that correspond to single points on the order parameter space. So, for example, if I take this point on S2 order parameter sphere, there is certain region in this space where this spins or unit vectors orient along that direction. And so now if you analyze all possible orientations that you could have within such toron field configurations, you will see that, yes, for every point you have a well-defined region of space corresponding to these orientations. And these regions start at the source and end at the sink, and describe uniquely this toron field configuration. While we were looking at the two-dimensional field configurations that I was telling you also, we could describe, uniquely by mapping from the physical space, which could be compactified oftentimes in some multidimensional spheres to the order parameter space. We also realized that all of the structures in 2D, for example, could be represented on a sphere S2, right? Because of that compactification property. And indeed, we know very well that the map of the world can be represented on a globe and vice versa. There is a stereographic projection that identifies, the relations between these different maps. And when we think about the topology, we don't worry too much about saying, certain parts of the world looking too big or too small in different representations, right? Because up to topology, that kind of stereographic projection works quite well. And so now this was in two-dimensional space. But if we would do such, so an important thing in here is, as you know very well, from the example of representation of our world, on a in different ways on a sphere or on 2D map, whenever we have circles on that sphere, they are also circles on a two-dimensional map of it that we get through stereographic projection. But if you would do an analog of stereographic projection of circles on S3 sphere to the three-dimensional R3 space, right, which is just five-dimensional analog of this stereographic projection, you would find them linked with each other, as depicted in here. And so this makes them topologically non-trivial. And this brings us to the so-called top vibration, which is a mapping from S3 to R3, where we also represent every circle that we get as a point on S2 sphere, right? So for every S2 sphere in here, we have a circle in a three-dimensional space, or in R3, right? And as you can see, this spheres, these circles link with each other. So for every pair of the points on the S2, we have circles in R3 that are linked with each other. And also, as we would look at the geometry, for example, we would take some points in here that have constant polar angle, right? So we would change on the azimuthal angles. The three images of these points in R3 would be tiling into a torus. And again, they have very beautiful topological properties. So it was Hope, I believe, back in 1933, who discovered that this three-dimensional space can be filled with the circles, topological circles, and also introduced the mapping from S3, the Hopf vibration. But topologically, this the Hopf vibration also corresponds to the topological solitons that we refer to as Hopfians. So while we could see that two-dimensional fermions in R2 or two-dimensional space with all possible 3D orientations of spins would have all orientations that correspond to all points on S2 sphere. And therefore, this mapping from R2 or corresponding S2 to the order parameter space fully covers this once. When we have a Hopfian, for every point on unit sphere of order parameter space S2, we have in R3 of our physical space of the material systems, such as liquid crystal or ferromagnet or ferroelectric, we have regions in space that have geometry and topology of circles or closed loops, right? For any 2 points on S2 spheres, these closed loops are linked with each other. That linking number is the topological invariant, which is the integer corresponding to the elements of the subhomotopy group of Pi3S2. So in order to identify if one has a Hopf vibration, we need to construct the pre-images. And we already discussed that these are the regions in the space where the order parameter takes the same value, right, which would correspond to a single point of the to a single point of, say, S2 sphere in this case, or the parameter space is a unit vector field. And so in order for us to have a Hopfian, these pre-images need to have the geometry and topology of closed loops, and this has to be the case for all points on the order parameter space. So, as I already mentioned, the points, the pre-images corresponding to different points are linked integer number of times in R3 and S3. That linking number is the topological invariant uniquely characterizing that Hopfian topological solid. So, well, we looked at many different spheres before, right? S1, S0, S2, they are all, somehow regions in space that are equidistant from the center. And this is also the case for the hyperspheres, right, that we could construct in a four-dimensional space. We just deal with a five-dimensional space. Well, it's a bit hard to imagine that kind of hypersphere, but geometrically it's very simple. So how do the Hoppians, topological solitons with different Hop indices look like? In here we see a structure of a Hoppian that's represented with the help of these cones in a two-dimensional plane that is perpendicular to far-field magnetization. And as you can see, you smoothly rotate the spins or unit vector magnetization field from center to periphery by 360 degrees in each direction. And just like for a solitonic ball, you can meet the far-field background after doing such rotation, right? But then in a plane containing far-field magnetization, we have a continuous structure that is everywhere well-defined, non-singular, but yet topologically non-trivial, similar to what we had also for two-dimensional skirmins, right? So now this whole three-dimensional configuration of which we saw here only two cross-sectional planes has the property that for every point on the order parameter space, we have a region in space in R3 that has a topology of a closed loop or circle. And so as we would take two different points on the order parameter space, they would correspond to different images that are linked with each other, and all pairs of points linked exactly the same number of times, which in this case is 1. So as we would go from, say, south pole of the order parameter space to the north, we see that for every constant polar angle, the preimages tile into the tori, just like the circles and the Hop vibration do. So topology-wise, this elementary Hoppian with Hop index Q equal 1 topologically is identical to the Hop vibration that we saw earlier. But geometrically it's different because the Hop vibration will take the entire R3 three-dimensional space, whereas the topological soliton here is compactified. It's compact. It takes finite space, and you can see in here that you can indeed tile these preimages within a finite volume where the North Pole corresponds to the far-field background that you will have outside of this localized region of the topological soliton. For every pair of these preimages, we have the same linking number that can be characterized based on crossings, and for this case, it's equal to 1. So again, looking at this geometry one more time, you can see that the space, three-dimensional space of this three-dimensional topological soliton is filled in with preimages corresponding to all possible orientations that you can have for the given order parameter characterized by this order parameter space. So now we, as you could see, looked at the topological solitons that are elements of this third homotopy group of S2 spheres. And the important thing is that the topological invariant is the linking number. While we looked at only elementary topological soliton, the Hoppian with Hop index Q equal 1, we can have any integer, as you know, this mapping would suggest. This is the Hop mapping. right? So, for example, when pre-images are linked two times, like forming this Solomon link for two, points of the order parameter space, we have a soliton that is distinct from this one or from uniform background in a similar way to how a torus is distinct from spheres, so you cannot morph one to another. The soliton described by these pre-images cannot be morphed to the one you see in here and vice versa. And so while the focus of my talk today was mainly on the pretty simple order parameter spaces that are described by unit vector fields or unit director fields, we can have physical systems like liquid crystals and other condensed matter states in physical systems that have more complex order parameter spaces. So, for example, we can have the biaxial nematic liquid crystals that can be characterized by order parameter space that is S3 mod Q, or these ones are with orthorhombic symmetry. But when we have, say, monoclinic symmetry, so when on the one mirror symmetry plane and one pi rotation axis are present, then the order parameter space is S3 mod Z2. And so for all of these structures, we can have different singular defects, line defects, or point defects. Some of them are allowed, some of them are not allowed. It all is determined by homotopy theory, the mappings from corresponding physical configurational spaces to order parameter spaces. And just as an example, in here I'm showing the topological solitons that are close cousins to these high energy physics solitons that you remember were described by third homotopy group of S spheres, pi 3 S3 equals Z, and Z in that case would correspond to different baryon numbers of nucleons. In this particular case, when we have biaxial liquid crystals with, say, monoclinic symmetry, the characterization, instead of, say, 3 pi fields, we have 3 unit vector or direction fields characterizing orientations in such a system. Okay, so in other words, while we will not go into details of discussing the complexity of singular and solitonic topological non-trivial field configurations in these more complex systems with high-dimensional order parameter spaces, I think what I discussed with you today should give you background foundation for being able to understand them as well. Thank you.